Thank you for the introduction. You're looking onto the motto, Foundry Goes Green. My focus will be on your CO2 reduction in the high-pressure die casting process with aluminium. So if you look to the CO2 emissions in the die casting process with aluminium, you see the main sources for the CO2 emissions comes from the aluminium itself, from the aluminium production from bauxite, or from remelting, refining of secondary aluminium, or then in the foundry from the melting process of the aluminium in the foundry. So the machines and the units and devices you can buy for the foundry equipment in the meantime are also optimized for less energy consumption. But if you look onto this diagram, even by omitting the aluminium production itself into CO2 emissions, the melting is the biggest energy consumer in the die casting plant. That's a study of Bühler, and there you see 54% of the energy that is used in a foundry plant is for melting and holding the aluminium. Then you have another 30% for the building and infrastructure, and about 12% for the running the die casting cell. If you go away from the CO2 problems, the other problems that foundries have are new challenges where you need stricter quality requirements that are arising from new applications for die casting. So the buzzwords here are autonomous driving. It's a big safety problem. Then water-cooled e-mobility components. If you have this 800-volt e-mobility units that are water-cooled, then you have to have very tight die castings. Then battery boxes, that's also a topic of safety during crashes. And then you have this big topic, mega casting, giga casting, that's well known from Tesla, or meanwhile also other car manufacturers. With this, your new ranges of applications, you need your defined mechanical properties, then your leak-free components, pore-free castings, where you have to look to gas and shrinkage porosity, and what's more and more important, especially for safety parts, is the traceability and the archive of process parameters that in the case of a crash, you see here on the right-hand side, these two guys in a car without any steering wheel, and if their casting breaks, then an accident is the result, and then you have to prove that your casting parameters have been inside the tolerances. And the next topic that is dealt with more and more in future is process optimization by artificial intelligence tools that can deal with a lot of different parameters in one calculation. So the most important approaches for CO2 reduction are therefore replacing primary alloys by secondary alloys with about 80 to 100% scrap content, and in the foundry the reduction of the amount of aluminium of aluminium that is melted, especially remelted, because it was scrap or remelt material. So if you look to the aluminium manufacturers that already works on recycling alloys with improved properties, so with this secondary primary alloys, you almost get meanwhile the same properties than with real primary aluminium alloys, and you see you can reduce the amount of kilogram CO2 equivalent per kilogram from the global average of 17 kilograms over the meanwhile European average of 7 kilograms to this 0.5 kilograms of CO2 emissions from this primary, secondary alloys that may be the solution for the future. In view of both of these mentioned fields, the new application or requirements for the new applications and also the sustainability requirements, it's up to the foundries to fulfill the necessary quality requirements even with this recycled alloys. And they have to reduce the amount of metals to be melted through reducing scrap, reducing the casting system or the mass of the casting system and overflow. And they have to optimize the documentation of the process parameters. And the next step is to reduce the number of startup parts. If you look to the diagram on the right-hand side, then you see it depends on the scenario. For 1 kilogram of OK part, sometimes you have to melt 1.4 to 6 kilogram of aluminiums with about 0.3 kilogram CO2 emissions for the melting process. And the influence you see here, your startup parts usually is 0.5 to 4% of the aluminium weight. Runner overflows 30 to 50, sometimes 80%. And the reject rate in this comparison, it's somewhere between 1 and 15%. And now we from FONDAREX thought about what can our peripherals devices contribute to reach this CO2 goals. So with an enhanced reliable vacuum, a sophisticated dye temperature control, and what's very important, a flexible system for decentralized feeding with squeezers. That means you can reduce the amount of or the mass of the runner system and the biscuit distinctively. And with an extensive process monitoring, it's possible to enable smaller runner biscuit systems. You can expand the range of usable alloys, especially with the background of this new recycled or low CO2 alloys. Then you can reduce porosity, improve the feeding performance, decrease the scrap rates, and it offers some potential for production on even smaller die casting machines. And last but not least, the FONDAREX equipment forms the basis for an effective use of artificial intelligence-based systems. So if you look to the area where our devices are applied, so you have during the filling stage, you have the vacuum system to get rid of the enclosed air and to fight against gas porosity, and to work against the shrinkage porosity. We have a cooling system, jet cooling system, advanced jet cooling system, and additionally, now at the Eurogus in spring, we introduced an intelligent squeeze system that is able to, for localized feeding, localized squeezing of the casting at up to 12 positions. So with the vacuum system, you can reduce the amount of gas and air in the cavity by up to 95% and get rid of problems with gas porosity and rejects because of gas porosity. Maybe you also can produce castings with your thinner wall thickness, and in this case, you also can reduce the amount of aluminium you have to use and to melt. So the typical vacuum system, here are the data. The big advantage of the FONDAREX system is that it is compatible with chill block, mechanical and hydraulic vacuum valves. Then the vacuum can also evacuate it in the short sleeve and the ejector box. The vacuum buildup can be adjusted, so it can be optimized buildup process of the vacuum, and the vacuum is measured for each channel and so on. So if you have any questions to our equipment, our booth is just behind here, behind the conference area. So you are invited to discuss all these topics in more detail. And so the typical machine size for the application of such vacuum systems is from 600 to 13,000 tons of clamping force. The next system that's fighting against shrinkage porosity and especially leakage around some cores or in threads, it's the FX Jet. It's a cooling system where you can cool with your very small dimensioned cooling channels with high cooling powers. It depends on vaporizing of water, and so it's a good use for your hotspot diameters from your 6 to 30 millimeters. And here you have an example with an inner nozzle diameter of 1.8 millimeters. You can realize cooling capacities of up to 2.4 to sometimes even more kilowatts. The system that is offered from FONDAREX is a modular system. You can expand this, retrofit it from 4 channels to 8 channels, and with this 8-channel version you can control up to 64 jet pins. So for each of these jet pins you can measure the volume flow, the amount of extracted heat, and the return flow temperature, and all this data are saved and can be evaluated for process optimization, or if it's produced for safety parts, you can store it for potential legal problems you will get in future. Okay, the next system we developed to fight against shrinkage porosity. It's an intelligent squeeze system. You see here on the left-hand side the porosity in the part with squeezer, and on the right-hand side without squeezer. And you see you can influence a quite big area of the casting with your pressing in this squeeze pin here during the solidification process. And so you can solve or overcome the problems with the shrinkage porosity you see here on the right-hand side. So your shrinkage porosity is generated by the shrinkage of the aluminium during the solidification. And if you have your wall thickness differences, then the area that solidifies last is mainly affected by the wall thickness of the casting. You can compensate this with cooling, but compensating with cooling is limited to about a factor of 2 in the wall thickness to reduce or to avoid shrinkage porosity. If you have your more differences in wall thickness, and usually you have this, then you have to work with squeeze pins. You see this in this schematic diagram. This small wall thickness difference between gate and casting you may compensate with cooling, and this bigger one at the top you have to press in a squeeze pin either directly in the casting or via a squeeze reservoir next to the casting, and then you can avoid scrap by shrinkage porosity. And And sometimes you have to design this runner gating and biscuit thickness system quite big and large. to be able to feed the casting via the plunger and casting system. If you work with several amount of squeezes, then sometimes you can make a very small casting system or runner system with low biscuit thickness, and you compensate the shrinkage of the aluminium by the squeezer. That reduces the amount of remelt material dramatically. So the advantage of such a flexible squeezing system is that you overcome the limitations you have if you want to feed via plunger, runner, and gating system. Then you have the possibilities to feed up to 24 critical areas. It's also a modular system, so the typical use is to up to 12 squeeze cylinders, but in an extended version you can also supply up to 24 squeeze cylinders with the system. The big advantage is that you can use the squeeze time, the squeeze pressure, individually adapted to the conditions of the die casting die for each of the cylinders to optimize the squeezing process. And because you don't need this much pressure generated by the plunger, you can sometimes reduce the size of the die casting machine. That's especially meaningful if you produce big structural castings with comparably low weight compared to the projected area they have. The data of the system are here. It has an independent hydraulic system, independent from the die casting machine. The advantage is that we can go up to a pressure of 320 bar. That means we can use smaller cylinders in the die casting die, because space in the die casting die for the cylinders is usually quite limited, and with this higher hydraulic pressure you can use the smaller cylinders. Then you have this individual control of each squeeze cylinder. That's the most important advantage. So you can set the start time of each cylinder individually, the squeeze force of each cylinder individually, and you can even set ramp for the force increase, and you can set the pressure holding time until the retraction. Then also here, like with the other systems, you can store, monitor, and record all the process parameters to be able to have a proper documentation of your production process, and you can work with these parameters in the process optimization, maybe with artificial intelligence tools. We started to do this for some applications. And with all, similar to the other applications, I told you we have an open OPC UA interface if you wanted to save this process data in an external database that saves all your production data. We only have to configure your OPC UA client, and then we can transfer the data in almost real time to your database. So as I told before, I see a big future in this use of artificial intelligence systems. And they will be improve the analysis and optimization of the die casting process quite well, because in the die casting process we have lots of parameters that we have to monitor and to have evaluate. And if you have a combination of 4, 5, 6 parameters that have to be in a good range, then it's very difficult to do this for an experienced employee. But with these AI tools, it's more and more possible in future. So we from FONDAREX, we won't develop an AI tool, but our task is to provide the data that are necessary to make this analysis and optimization. So as your summary, I can say that you're taking up the new challenges for the new product ranges while reducing the CO2 footprint of the high-pressure die castings. The use of innovative peripherals is quite important, and your FONDAREX will provide you with a comprehensive support through advanced equipment and also with expert consulting services. As I told you before, you can contact us at the booth just behind. Here you have your small extract from the client lists. And if you want to have contact, then either directly with FONDAREX or with our Polish representative, Andrzej Fiedler, and his company, Cast Metal, also at the booth behind. And if you want to have a copy of this presentation, please send me an email or give me a visitor card, then you will get the PDF of this presentation. So thank you very much.